gentlemen. It's a pleasure for me to have the chance to present you today the ESA ANTEX. Thank you for the introduction, and I also want to say thank you to my co-authors, in particular Florian Dilsner, who generated this file, and I think he's the right person to thank. As everybody knows, and as also shown by the previous presenters, the information of satellite antenna phase center offsets are indispensable for precise navigation, in particular for precise orbit determination, as it provides the link between the center of mass and the phase center where we transmit the signal. However, due to the lack of manufacturer values in the past, they have not contributed to the ITF scale. But this has changed, or at least the possibility has changed in December 2016, when Galileo, as a first GNSS provider, published PCOs and PCVs via the European GNSS Service Center. And this metadata, as also Marco mentioned yesterday, is updated regularly whenever new satellites come available, so that the data is there to use it. So for the third IGS reprocessing campaign, the Galileo phase center calibrations were available for both, for the satellites and for the stations and ground antennas, and so ensured or enabled the consistent processing of Galileo observations for the first time. However, the IGS GNSS solution showed an offset to the ITF in the order of 0.68 ppb, as shown in the publications, and is due to the decision that the ITF is based on VLBI and SLR. And this required a rescaling of the GNSS satellite Z-offsets, but it also should be considered that at the same time the estimated SLR range bias have been fixed in the combination. As a consequence, in order to maintain the consistency between the IGS products and the ITF, the ground calibration values of available for Galileo, but also for GPS Glo 3, had to be adjusted, and for Galileo it was in the order of 16 centimeters. The exact value is given in the slide, and also in the respective IGS mail. But for us, when we consider the accuracy of the ground calibration, which was also confirmed by other publications, which should be in the order of 1 centimeter, we at least consider it a bit not sensible to adjust the Z-offsets by an order of magnitude above the uncertainty. And also considering the uncertainties we have in the ITF, and also what we have in the ground antenna calibration, we have seen the presentation yesterday on the consistency of the laboratories or the calibration institutes contributing to the IGS ANTEX, which was in the order of 4 millimeters. This also gives a bit of doubt if the GNSS satellite phase center offsets are the right place to adjust for this scale offset. And also maybe to show a bit the significance of this offset we have between the IGS solution and the ITF. So also the offset between ITF 14 and ITF 20 was already on the level of 0.4 ppb. This brings me to the motivation we had to look into an ESA ANTEX, because we are advocating to use all ground calibration data we have to contribute to the scale of the ITF, and this also includes the GNSS calibrated values we have available. And as mentioned on the previous slide, in this case, or in this respect, we don't see, or I see a bit questionable to adjust all the offsets in the IGS process. It's also in view of the upcoming Genesis mission, as also shown in the previous presentation, if we can calibrate phase center offsets of the GNSS satellites by using LEO satellites, then because of the gravitational force we have on the orbit, it's the same the other way around. If we are not using the proper values for the LEO satellites together with the highly accurate calibrated values for Genesis, we will see the differences, and this will impact the process in the end. Another point why we say it's important to bring this point up, I think the scientific community, including the IGS, requested the publication of the metadata for several years, and a lot of effort was made on ESA side, but also on the provider side to get these values published, which was not that easy. And we see that this gives a bit of a wrong message to the service providers when we ask for more metadata to be published, if we say we cannot use it. And last, or another motivation to look into ANTEX, not looking at the calibration values we have here, but is the inconsistency we have in the up-to-date IGS ANTEX file. We were looking into multi-GNSS processing, as we have also shown on the poster, so our products are multi-GNSS in future. And we had the inconsistencies in the beta values, which we take from the IGS 14, which I will show later on, and this also gave a bit of motivation to look into. And finally, to preserve the consistency with the GNSS providers, who may use their own calibrations also to generate a navigation message. It's not of major importance, but already yesterday we heard that there were requests to publish the values used to generate the navigation message. Yeah, maybe quickly on this slide, this was how the Galileo antennas were calibrated. I think the slide was shown before by Francisco Gonzalez. The values, the antennas were calibrated independently for IOV and FOC by the respective manufacturers. Done for each of the Galileo satellite antennas, for each of the individual frequency bands. And yeah, as shown in the publication also presented by Oliver, we have a very good consistency between the individual frequency bands, between the individual frequencies, with exception of one satellite. But this gives confidence in that the values make sense. Let's come a bit to, or let's explain the strategy we have selected to generate the ESA ANTEX. So we use dual frequency atmosphere free data in an IGS-like processing of all GNSS constellations available for 9.8 years. We used 4 years for BeiDou L1, L5, and we rigorously combined all the parameters we had, or we set up in the database. For the constraints, we use the phase center offsets and phase center variations available for Galileo, for GPS Block 3 and QZSS. We haven't used yet the Block 2F because a lot of effort has to be done to make it usable. Thanks Oliver for working on this. But we also used or fixed the horizontal PCOs for BeiDou. We fixed the vertical or the set component, as we will see later on, because there are significant discrepancies. We also adopted from earlier estimation the phase center variations of BeiDou, and the horizontal PCOs and PCVs for Block 2 we adopted from the IGS ANTEX. We freely estimated the Z-offsets relative to the Galileo scale for all the systems, and let the network scale free. What we show here is to show the consistency of the GPS Galileo scale. We see here the differences we get when we estimate the Lockheed Martin values we have, when we estimate the phase center offsets in Z direction for the Lockheed Martin satellites or antennas. And we see the deltas are in the order of a few millimeters. Small compared to what has been the adjustment, and this was also the decision to use the original manufacturer values in the ESA ANTEX. We also see a good consistency if we use the ESA ANTEX for between the Galileo and the GPS scale. We compare this with using 1 year of ESA data out of our processing where we do the individual constellations. We see it on the top, so the difference in the scale is about 0.16 ppb between the GPS scale we achieve with the ESA ANTEX and the Galileo scale. Have a quick look at the estimates of BeiDou, the set of estimates of the MEO satellites, which was the most significant difference we got to the manufacturer values. Here we see an offset of around 40 centimeters also with respect to the IGS 20. And this has significant impact on the satellite orbit, in particular on the long term. And yeah, let's have a look at the orbit quality. So this shows the day boundary overlaps of a 4 months IGS-like processing using the ESA ANTEX. We have done it once with the ESA ANTEX and done it with the IGS ANTEX. So we see in green the 3D RMS of the day boundary overlaps, residuals, using the IGS ANTEX, and in red the ESA ANTEX, and we see an improvement for almost all satellites, but a significant improvement for BeiDou, where it's a factor of 2 reduced the RMS at the day, more consistent. This becomes even more obvious if we look at the residuals itself. We see on the right-hand side the residuals with the IGS ANTEX in purple and with the ESA ANTEX in green for Galileo, and on the left-hand side for radial, and we see the significant improvement in the orbit overlaps. Let's have a look at the scale. So how does this affect the scale? So we have done a test using also our products we have available already at ESOT. We used 4 years of multi-GNSS products. We used the daily norm equations from this processing, or the processing called TEMP, maybe not to confuse with the satellite, it's the name of the processing, there's also a post on it. We used introduced the station coordinates taken from the ITF-20 and the station coordinates from the DTF. But for the velocities, since it was a quick test, we stick to the velocities of the ITF, so benefiting a bit the ITF and using the velocities of the and PSTs of the ITF. We left the scale and the origin free, an estimate to estimate, and oriented the solution to the ITF and the DTF, and then compared or looked at the scale we achieve. So we see on in purple, we see the scale offset with respect to the ITF, which is in the order of 4 millimeters, which is exactly what we expect because this was what was adjusted before in the phase center offsets. And we see the scale difference with respect to the DTF, similar result as what Oliver presented, so it matched quite well if we use the original manufacturer values and align it to the original manufacturer values to the scale of the DTF. This brings me to the conclusion. So accurate phase center offsets and variation have been published first by Galileo, but are now also available for other constellations, for GPS Block 3, for QZSS as well. As ESA, we advocate to use these values for the future ITF realizations and to consider the GNSS contributions for the determination of the terrestrial state scale, and therefore also to use the GNSS, the Galileo and the ground calibration of the other GNSS in the generation of the scale. Maybe some words to the ESA ANTEX. As I've shown before, the scale is well aligned to the DTF. The ANTEX is fully consistent over all constellations and is publicly available on our webpage. Maybe one point for the discussion, we see no need to have perfect satellite antenna phase center offsets, but we could use it as a parameter with the respective uncertainties, similar as we do it for the local tracks. This brings me to the end of the presentation. Thank you very much for your attention, and also thank you very much for all the contributions from the coaches.